Hello everybody, welcome back to part 2 of our circular motion video and another episode of the problem solving series. So as I mentioned in part 1, that did cover all of angular kinematics and how we go from angular quantities to linear quantities, and I showed an example problem looking at that. And then in this video, we're going to go through just looking at centripetal acceleration and centripetal forces, and I'll also show how the previous video's material connects back to the problems that you'll see here. So a lot of the times these are interchangeable or they're even in the same chapter. So both the example problems that I'm going to go through only have one question, but will have multiple steps that involve rotational kinematics and the centripetal concepts that we're going to talk about here. So let's get started. Centripetal describes a direction, and that direction is going to be radial, so it's going to be radiating out from whatever center point our circle is. Centripetal acceleration for an object that is moving on a circular path is always going to point towards the center, and it's going to be equal to the tangential velocity squared divided by r. So that's mainly the only new equation that you learn in this part. One of the things I will mention is they don't typically put like a subscript t or anything on that velocity in when they write this out, which I'll pop it over here. So that's usually something that they expect you to have memorized, that the centripetal acceleration is the tangential velocity squared, and that velocity is going to be constant. So as you're moving around the circle, no matter what point of the circle you're at, your velocity vector direction will change, but the size of that vector is going to stay the same, and that v squared divided by the radius equals the centripetal acceleration, which will always be pointing in no matter what point you are on the circle. So what this then means for us is that since now we have an acceleration, we can look at how forces are involved with providing that acceleration to different objects. So when we talk about the centripetal force, people shouldn't be talking about it and calling it the centripetal force, because it's any force that's pointing either directly towards the center or directly away from the center of a circle. So anything moving along that radial axis is a centripetal force. So it's a class of forces, not a specific force. And then since this is all happening on that same radial or centripetal direction, or dimension, however you want to call it, then we can use Newton's law to say that the sum of the forces along the centripetal axis equals mass times the centripetal acceleration. So I'm going to cut over to two different examples that again are going to pull concepts from angular kinematics and concepts from using these centripetal forces now and knowing that we can use Newton's equation in this way, and then how centripetal acceleration relates the Newton's equations to the tangential velocity. So that kind of gives a hint of what things are going to be at play here and kind of the steps we're going to have to make. So let's jump into example 1.
Okay, example problem 1. A bug is sitting on a rotating disc 3 centimeters from the center at a rate of 45 rotations per minute. If the mass of the bug is 2 grams, what is the coefficient of static friction? So I have asked a multi-part or multi-step question all in this problem, but it's going to show the way that we can relate the rotational kinematics to centripetal acceleration and then centripetal acceleration to forces. So first let's write down what we have. And we'll draw a picture. So we have our disk. There we go. And we'll put our center is here. We'll say our bug is about here. And this distance is going to be our radius. So this guy will be traveling on a smaller circle within the bigger circle of the disk. That distance 3 centimeters. We'll write as meters, so we would divide by 100 to get that into meters. And then our angular velocity is that 45 rotations per minute, and we can convert that by saying 2 pi radians over 1 revolution and 1 minute divided by 60 seconds to get that into radians per second. And that gives us 4.8 radians per second. Okay, the other thing we have is the mass. So that's 2 grams. So we would divide that number by 1,000 to get that into kilograms, and that should be 0.002 kilograms. Now, we do have this top view. So if we were to add on here, I'm going to go ahead and erase where I drew that R since we already wrote it down. I guess I could write it over here just so we have it. And we're going to have our acceleration AC pointing inward. And as far as our forces go, we're going to have static friction pointing inward this way. And then if we wanted to get a side view as well, just so that we have the full picture, we would have our force of gravity pulling us down and our normal force pushing us up. So sometimes it's useful to have a side view and a top view, or just multiple views of the same situation, depending on what's going on in the problem. So if we start off with what we're interested in solving for, so that's going to be our coefficient of static friction, which means we need to first find that static friction force that's pointing along the centripetal direction. If we use the sum of centripetal forces equals mass times centripetal acceleration, the only force we have acting in the centripetal direction is our Fs equals mac. Then we can substitute in that Fs is mu s times Fn, so that's just the equation for friction. And then looking at the sum of the forces from the side view, so the sum of the forces in the y and setting those equal to 0, since this bug is not coming off the turntable or falling through it, that'll give us that our normal force minus Fg equals 0, or that Fn equals Fg, which is equal to mg. So we can go ahead and make that substitution. Mu s times mg equals mac. We can cancel out an m from both sides, but after we do that, we've reached the end of the road of what we could do with this equation by itself. So we've gotten to a point where we have our unknown that we're interested in, mu s, but we also have this other unknown, ac, that we need to figure out. So ac is our centripetal acceleration. We have an equation for that. It's v squared over r. But then if we look at this, we can see that we don't have v, but we do have angular velocity, and we could put that in terms of tangential velocity, which is the v that's in here. So it's never usually included, so I'm just going to write it in a different color. But just so that you guys know that that is the tangential velocity, but that will be a concept that you're expected to memorize when using these equations. So we'll have our v tangential equals omega times r, so that's just converting from angular to linear. And then you could either go ahead and just start substitute in variables all the way back. So this would go in for here, and then this would go in for here, and then you can rearrange for omega s and solve. Or you could put the numbers in starting with our VT equation and plug in as you go. So that's that substitute and solve from the guess method in action being interchangeable. I'm going to use variables because I think that's what people are less comfortable with, and It is a good goal to get comfortable with using just variables when doing your physics problems because it can help make things easier to cancel out and solve in the long run. So we're going to substitute in omega r, and for this vt squared. When we do that, we'll get omega r quantity squared over r, which would be omega squared r squared over r, and we'll have one of those r's cancel from top and bottom. So we get AC is equal to omega squared times r. And then we're going to put that guy in here, and we'll get mu SG equals omega squared r. We'll divide both sides by g to get our mu s by itself. So mu s equals omega squared r over g, and then we can go ahead and substitute in 4.8 squared times 0.03 divided by 9.8. And sorry, the space is getting weird, but from that I get 0.0071 is going to be our coefficient of static friction. Example problem number 2. A 60 kilogram person is riding the gravitron. What is the minimum velocity necessary to keep them from sliding down the wall? The coefficient between their clothes and the wall is 0.01. Okay, so I am presenting you with another multi-step to get to the answer problem, but this time going in a slightly different direction, and we're going to be using our centripetal forces and our centripetal acceleration. First, I will draw the picture for you guys. So again, I'm going to do a top view and the side view for this case. So our top view is going to be the circle. This person is pressed up against the wall, and we're going to have normal force pushing in, and our centripetal acceleration is also pointing inward. And then on our side view, we're going to have mg pulling us down and the force of static friction pushing us up. We've got mass equals 60 kilograms, mu s is 0.01, and we are solving for v. So we can say the sum of our centripetal forces equals mass times AC. We can say the sum of our forces in the y is going to be equal to 0. That's what we're trying to get to. And then our only centripetal force is going to be normal force, so we're going to have F normal equals MAC, and then vertical will have force friction minus mg equals 0. And for force friction, we're going to substitute in that is mu s times normal force minus mg equals 0. So we'll get that mu s times normal force equals mg. We will divide out mu s to get an expression for normal force. So that is mg divided by mu s. We'll move that into our other equation. And then I'll also take this time to substitute in that mv squared over r. Ooh, I forgot to give a radius in this problem. That's important. We'll set the radius equal to 10. We do have masses cancel. So we'll get g over mu s equals v squared over r. We'll multiply both sides by r. And then we'll also, well, I guess I'll do this step by step. So we'll get r times g over mu s equals v squared, and then we'll go ahead and take the square root to get rid of that squared. We can plug in our numbers. 10 times 9.8 divided by 0.01 square root equals v, and that should be about equal to 1. So if I swap out and use my estimate that I love to use, this will come out being 1 meters per second.
Okay, and there you have it. So that is my take on circular motion. The only thing that I guess I'm leaving out a little bit is going to be brought up when I do the global gravity equation. So that is going to be my next video. And that will involve a little bit more of that concept of period and a couple other implicit pieces of information that you are going to be expected to know going into an exam most likely, and that I don't think will be provided to you on an equation sheet. So we'll talk about a couple different things there, and that big G gravity equation, just there's a little bit of troubleshooting that has to go into it. So I will leave you on a cliffhanger for that video, and happy physicsing until then. Howitzer, you've been so sleepy lately. Did you have fun at daycare today? You still gonna say bye to the kiddos? You give them kisses? You give them kisses? Oh, thank you.